Dear students, welcome to another class of mathematical methods in physics. This is the second part of the lecture for the week from 4th to 9th of October 2020. Today we are starting a new topic that will constitute of basically the 14th chapter of the book that we are studying, and the topic starts with the analytic functions. Basically, I will use the book that I have recommended to you, and these notes by this guy, Dr. Jeremy Ul-Haq from MIT. So these notes are very well written, and I will also share these notes with you. So let's start. First thing that we are going to learn today is analyticity of a function. What do we mean by the analyticity of a complex function? So to understand when we say that a function is analytic, first of all we have to consider what do we mean by a derivative. So normally you know what the derivative of a function is, and how you are computing the derivative for various real functions before this course. So now let's see what a derivative means in real world and in complex world. So a derivative is defined normally by this equation. We say that a derivative of a function f of z, if we have a function f of z, a complex function, we say that its derivative is given by this formula, that we increment function a little bit, and then we increment the variable a little bit, and then we define this limit that this delta z approaches 0, and if this exists, if this is defined, then we say that the function has a derivative. If this is defined means it's not infinite, and what this also means, it is defined as a limit. Okay, so first I tell you what does it mean by delta f. So delta f basically is a small increment in the function itself. So we write it f of z plus small increment inside those variables, and then we define it as an increment. So this is basically, we have to subtract it from the original value. Okay, and then delta z is delta z, and if we could apply this limit, that means this exists. So this is a bit complex. Let's go back to the real world and let's see what does this mean. So for example, if we have a real valued function now here, so this is, we have an f of x that we have that is a real valued function, and it is given by this curve. We have defined f of x given by this curve here, and suppose we are trying to impose a limit that x approaches x naught to this function. So this is a function, this whole curve is a function, and we are saying that x is approaching x naught, and let's see if this function is defined at this point or not. So we can approach x is equal to x naught in two ways. So we see this curve, so we have to reach this point here, and we can do it in two ways. So either we can approach it from higher values in this direction. We call this approaching from x is equal to x positive or whatever you call it, higher values. X approaches x naught for x greater than x naught. And we can also approach from this direction, and then we say okay, x is approaching x naught for all x which are smaller than x naught. So whatever we do in this case of a real valued function f of x, this is not a complex function, this is a real function, anything like f of x is equal to x square, for example, it can be like that, but we haven't defined which function is that, just I want to say that this is the case. So what will happen that whatever we do, when we approach x naught, the function has uniquely one value that is defined according to this line. So this is f of x naught. So our direction of approach does not matter. Whatever we do, we reach the singular value, and this is true for any other point. So you can define any other point here and do the same point, do the same treatment, or here. So it will not matter. You will always get f of x naught. And if this is the case, we say that the function is defined in this region of x is greater than 0. So f is defined and the limit exists. We say that f of x is defined for each value of x and for each point on the curve f of x, the limit is x approaches x naught exists. Limit exists, or sometimes we call it limit x is equal to x naught converges for all points. For all points on the curve. So this is the definition of a limit, or whatever. We say that the function is regular sometimes. We say these things in a number of terms. So we say that the f of x is a regular function, or we say that f of x exists. Sometimes what we say that okay, f of x exists. But in complex numbers or in complex theory, this thing is not exactly what it happens. So let's check, for example, function. Sometimes everything goes very well, and sometimes this does not happen. So let's do an example that is done already on this page. So I just repeat it. So let's say that we have a function in complex variables. F of z we have is z squared. So we now have to determine that whether this function is a regular function or not. Determine if it is a regular function. So what we do, we just take derivative and see what happens to it if we approach various points on this curve, this curve from various sides, from different sides. So let's take the derivative. So we write the derivative as f prime of z that is uh, d of dz. So we are defining derivatives from first principle, what you call it. We are not defining just like, okay, d of dz is equal to 2z. So at the end of the day, we will get the same result, but uh, we are trying to understand the fact, so we have to do the whole process. So we define the limit for the derivative, that is f of z is equal to limit delta z approaches 0. So we increment the function according to our definition, z plus delta z whole squared minus z squared over delta z. Okay, so this is the definition, and then we just open this square here, and we are left with now limit delta z approaching 0, z squared plus delta z squared plus 2z delta z minus z squared over delta z, and this z square is cancelled with minus z squared, and we can take limit z delta z approaching 0. We take delta z common from the top, so we are getting delta z plus 2z, and from the denominator, so again we cancel these two terms here, and now we apply the limit. So now when we apply the limit to this thing here, so delta z goes to 0 means we are left with only 2z. So this is simply the derivative. Now tell me one thing, think in your mind and tell me if this value, this 2z value, it depends on path or not. Whatever value we put for z, for example, we are approaching the function from negative side or a positive side, so will it change the value? Will it vary the approach? Whatever we do to the function here, it does not matter. We will always reach the same value. Whatever we do, we will always reach the same value. So we say that this function exists, or this function is a regular function on a complex plane. So because z the final expression does not involve anything pertaining to delta z. That is the only criteria. So if there would be a term that would contain delta z, then it would matter a lot, and then we will have to think, well, what we do, how to reach it. But since it's only in terms of z, so we say that, okay, this function f of z is a regular function. Okay, it's a regular function, but can there be some functions which are not regular? Yes, they can be. So we do the example. Now we have a function defined by z static or z bar. So we have a function that is given by f of z equals z static or z bar, the complex conjugate of z, where z is x plus iota y. So z bar would be x minus iota y, the complex conjugate. So when this is the function, then we apply again, we want to define the function, so we do apply the formal definition of derivative, and then we say, okay, we are approaching delta z. So let's do it. We have for derivative at any point, we write it like this: limit delta z approaching 0, f of z plus delta z minus f of z over delta z, and f of z plus delta z is delta x, sorry, x plus delta x minus iota y plus delta y, this guy here, and we just put it in. So we have f prime of z equal to limit of delta z approaching 0, delta of x, x plus delta of x minus iota y plus delta y, and minus original x minus iota y, and divided by delta of x plus iota delta of y. This is delta z. Okay, now let's define this function at z is equal to 0. Define this function at z equal to 0. So we get f prime of z which is limit, f prime, not z but 0, because now we are defining it as 0, at 0. That would be limit delta z approaching 0. So we put x 0 everywhere, y 0 everywhere. So what we get here, x0 means only delta x, y0 means only delta y, and this guy will also go away. So we get delta x minus iota delta y divided by delta x plus iota delta y. This is basically this guy here in printed form. So now we see, okay, we have defined a point, and we want to see if we want to define a derivative at a particular point, x z is equal to 0, if we approach from different directions to that point, will it be the same or will it be different? So let's define now how we can approach. So let me do some more things here. So let's define a complex plane. So we are some at z is equal to 0 means we are here in the middle of this plane. This is 0, and we want to define we want to see if we approach z is equal to 0 from various directions. So what can be the directions? So we can move along the x-axis here to 0. This is one direction. Or we can move along the imaginary axis here in this direction, because at the end of the day we want to reach this point. So what will happen? Let's see. Let's do it along the x-axis. So when we approach along the x-axis, so then what is the case? Delta y is 0. So if we are coming along this direction, so there is no on this. So on this line, delta y is 0. There is no change in the y coordinate. So we are only changing. This is we have already set equal to 0. So when we set this equal to 0, so how our equation that we defined for the derivative, how will it be affected? So our equation is this one. So here we have set for the first case we have set delta y equal to 0. So this is modified as, for the special case, f prime of 0 is now limit delta x approaching 0. So our limit is modified now, and delta y is already 0. So we are left with delta x over delta x. Okay, and then they two cancel. Delta x and delta x cancel. So this is equal to 1. This is equal to 1. Fair enough. So we are getting a value of 1 when we approach the 0 from a side, from an axis. Let's do it another way. So we now approach the same point 0 using some other direction. So I define it like this. So we are now approaching this point from positive y direction that I already defined. So this is our 0. So here we have to set delta x equal to 0 in that equation, in the primary equation for derivative, this equation here. So if we set delta x equal to 0, so we are left with the derivative definition now becomes, so now how we apply the limit. So we say that limit delta y now approaching 0 f prime of 0, this is equal to limit delta y approaching 0 minus iota delta y over delta y, because we have put delta x equal to 0. We have defined approach like this. So now again delta y and delta y cancel, and we are left with the value, sorry, there is iota underneath also. So we are left with the value minus 1. So we have now f prime of 0 equal to minus 1 when we approach from positive y direction. So we are getting different values of the function if we change the limit, and this is a problem. We cannot have a function which has a derivative which changes values when we change the direction. So this is not defined. So we say that the limit does not exist and the function is not a regular function. What we say? That the function f of z, that is x minus iota y is not a regular function because we are getting different values from approaching from different directions. This is the thing that you should keep in mind, what we mean by applying a limit and the regularity of functions. In complex analysis, a function is function only, well-defined function only, when we approach by whatever means, whatever path, it should give us the same value. So for example, if we are defining function, defining a derivative at this point, so whether we are approaching from this direction, this direction, this direction, or along this direction, it should always give us the same value, singular value, and only then this function is defined. And only then this function is defined. So or what we call it, it has a complex derivative. The function has a complex derivative. I should write this definition somewhere on the screen so that you should be comfortable with the definition. So I write it here. A function is said to have a derivative when it gives single value, whether one approaches this function approaches a point on its curve so just remove the word whether. So if one approaches a point on its curve from any direction. And if this is the case, if a complex function has a derivative, this is called also analytic function. This is also called analytic function. This is the standard definition. Now, because the problem is that complex functions are defined not by a single variable but two variables, so we need to be careful what do we mean by this analyticity approach. So if now we have two variables, so in the example of the real valued function we had only one variable. In terms of complex functions we have two variables, x and y, and when we have this kind of a situation we cannot check the derivative very easily, if the derivative exists or consistent or not. So for that we will need some other tools to accomplish, but we will see them in later lectures or later lecture today. But today I want to define some basic definitions that you need to know when we are using analytic functions and topics like that. So let's move on to those definitions. So these definitions you must remember by heart whenever we want to study complex functions. So first definition is open disk. This is I introduced you what do we mean by a disk. So I told you that if we are given like an equation x square plus y square is equal to is greater than a square or less than a square, then it defines a disk. So if it's, for example, it is x square plus y square is less than 3 squared, that means it's a disk with a radius less than 3. And if it's greater than 3, that means it's a disk which has the middle part missing. And that we discussed in the last discussion session. So today I will tell you more about disks. So first of all, we define an open disk. So an open disk is something that has a well-defined area. So if you have a set of points, you have some set of points as such a set which constitutes a circle like this, and then we call this circular area a disk when we have a well-defined limit to it. So for example, in this disk, what you see on your screens, we have a well-defined area, that is the area of the circle, the area of the disk which has a radius of r. So mathematically, I told you even before, we define such kind of area as z minus z naught is less than r. So we define this as z minus z naught less than r. So here r is the radius. Just pay attention here. You have to pay considerable attention to this concept because it's not so trivial. You have not read it anywhere about anywhere in your course about these kinds of things. So remember, z naught is the center, z naught is the midpoint or center of that disk. And when we use this kind of terminology, that z minus z naught or z minus z naught modulus is less than r, so it always means that we are talking about, okay, so I should use a different thing. Okay, I should use bluish here. So this one, not this one. So roughly this whole area. Whenever you see such inequality, you should always keep in mind that this is the open disk with center at z naught. Z naught can be 0, 1, 2, 3. It does not matter if it's actually 0 or not, but this inequality will define it. Okay, and this is called an open disk. Another important definition is an open deleted disk. This is a similar concept that defines that you have something and you have something that is missing from inside. So for that open deleted disk is something that we remove its center from it. So we drill a hole through the center of this disk. Then we call it, okay, this is a open but a deleted disk. You see from this figure, I don't know if I can zoom it properly or not. Okay, let me see if I can zoom it easily. No. Okay, but you can see there is a small white dot inside it, which shows that we have removed the center of this disk. And then how we write it mathematically? Mathematically, it is written as z minus z naught is greater than 0 but is less than r. So we have increased another inequality into this this condition. So for an open normal disk, we don't have to be, this should not have to be greater than 0. So 0 is included in it. But in a deleted open disk, so the center is missing. So this means that every point is included in it except z equal to z naught or 0, whatever you call it. So sometimes we also call this as punctured disk. So there is a puncture, there is a hole in it. So if we know these things, we know these definitions, we can understand complex analysis very easy. Complex analysis becomes very easy, and we don't have to go back and forth again to search for definitions. So now there is a related concept. So if you are now familiar with open disk and an open deleted disk or open punctured disk, so we can now define an open region, an open area. So an open area does not mean an area that is open, like you can go anywhere. So in complex analysis, it has a proper definition. So pay more attention, be relaxed and pay more attention. So an open region, there is a definition written here, if you can see. So it may seem like a complex definition, but it is very easy if you see. So it defines that it's such an area that each point in that area can be surrounded by an open disk. What it says, each point in this area, each point in an open area can be surrounded by an open disk. So very easy definition. You know what is open disk. So we are given two examples. One is this one is this one. So just keep in mind that this dashed line is not a part of this area. The dashed line is not included in this area. So now whatever point we take inside this area, so couple of points here and one point here, they are given. So we can form a small disk around it. So whatever point it is, for example here also. So we can find a small disk here. We can also find a small disk here, find a small disk here. So this is a good example of an open area. Physically speaking. And now let's see another area that is given on the right of your screen, part B. So here this solid line is a part. This line this line is included in area B. So now if this line is included and we take any point on this line, we cannot make an open disk that is inside this area. So the some part of that disk will go outside. You see how interesting is that? Some part of the disk will always be outside this area. So this is not an open area, this is a closed area now. So you see, these are simple things on the first sight, but they have very interesting consequences. And I mean, it's later we will see that how long it will go, and this understanding will go in our understanding of complex numbers and complex functions. So if you can understand this thing, you can understand later concepts very easily, I guarantee you. Now I give you a small introduction about mapping, and then I will end this lecture. So any function, basically it maps from one kind of coordinates to another kind of coordinates. Something that is in one type of coordinates, it maps it to some other kind of coordinate. For example, if you have a function, for example, let's talk about real functions first. So you have f of x is x squared. This is the function that, for example, you know. So for each value of x, you will get something x squared. So you first define a line which is x, this line. Okay, so I just draw one line. So you define a line for x. So if you put x is equal to 1, so if we have 0 here, 1 here, 2 here, 3 here, so if you put x is equal to 1, so it draws a line corresponding to x square, another line corresponding to x square. So if you have x is equal to 0, so this function maps basically x is equal to 0, it will be mapped like this. X square will also be 0, so this is the mapping. And if you have x is equal to 1 here, so it will map on this this line a point that is again 1 here also. F is x is 1, so it is mapping another point here. And if now you put x is equal to 2, then it will map x square equal to 4. So this is 2, 3 and 4. So x is equal to 2 maps 2 to 4, this point here. So every function shows this kind of a mapping in any case. This is a standard definition of a function. Okay, so there is, for every value of x, there is a unique value on the line that is defined by this function. Okay, so in complex analysis, in complex functions, this terminology is also true. So for analytic functions given by this figure, so for example, we are defining some point z0 for a function z, and it will map another point omega naught in the plane defined by the function. So if we are defining function like this, we are defining f of z equals omega or w, and if there is a point z0 on the complex plane, because now you know it has two variables, no? So for a single variable it is a line, as you have seen here, x, so it will define a line, but a complex number is a function of two variables, x and y, so it will define a plane. So on here it's imaginary part, here is real part, imaginary im of z, real of z. So previously we used to write x and y like this, but you can also write real of z and imaginary of z, and it's the same. And the complex function is like like very interesting thing. So original complex number is also in 2 dimensions, and the resulting function is also in 2 dimensions. So you see the relationship here. Here one line, line to line, point to point on a line. Uh, in in terms of complex numbers, we have to define from plane to plane. So we are approaching a limit z naught in the complex plane of the real numbers, and the function also approaches a singular value omega naught. So this is getting mapped, z naught is getting mapped to w naught or omega naught. So this is a relationship of a function to its values or its so if we call this a domain, so you have read about maybe domain and ranges. So this is a domain and this is a range in terms of real values, and normally we call this mapping. What we call this? We call this as mapping. And it's very interesting to see that for analytic functions, for each value of z naught there is a corresponding value w naught. So it should be unique one. And sometimes it's not unique, and when this is not the case, then the function is not analytic. For example, the same function z over okay, so previously it was just z prime, now the function is z over z prime, so that is x plus iota y divided by x minus iota y. And if you now choose a point z is equal to 0 and apply limits, so you will again reach two different points. One time you get 1, the other time you get -1. So the limits do not match, so again the function does not is not analytic, or is not a regular function, is not proper function that we will deal. So we will always deal with proper functions. So that is it. The lecture has become now already 47 minutes, so now I have to stop. So I hope you have got some new definitions and some new ideas from today's lecture. Next time we will explore the ideas of analyticity in more details, plus I will give you some exercise questions so that you can apply them and see how the things go. So till then, bye bye.